In previous videos we have discussed models for variants of a furniture production planning problem. Let's go back to our roots and have a look at our very first basic model where tables and chairs were produced. With the knowledge we have gained up to here, we can try to formulate just another model for this problem. Think about the transportation problem. Can the transportation problem help us to formulate a model that describes the furniture production problem? Well, let's see. To produce tables and chairs, we need small parts, 2x4s and 2x2s. Let's look at the 2x4s first. Assume that we have a supplier that delivers 2x4s. This could happen from our own warehouse where 2x4s are stored, and in this sense we are our own supplier. I mention this to highlight that words like supplier can be reinterpreted. This supplier can deliver to two customers. Again, the word customer can be reinterpreted too. In our application, a customer is either our workshop for tables or our workshop for chairs. The demand of these customers is 2T. If T tables are produced, and C if C chairs are produced. Maybe there's a dummy. The demand of the dummy would be 6 minus 2T minus C. We can now introduce decision variables that represent the number of 2x4s that are transported from our storage to the table workshop. Or to the chair workshop. Two by fours can be transported from the storage to the dummy. This actually means that these 2x4s remain unused in reality. Let's turn to the 2x2s now. As before, we can think of our storage as a supplier who delivers 2x2s. The limit is 8. Our two workshops for tables and chairs are a source for demand. The demand is 2T if T tables are produced, and 2 times C if C chairs are produced. Again, a dummy represents the fact that some 2x2s may not be used. The demand of that dummy would be 8 minus 2T minus 2C. The decision variables for the quantities are Z21, Z22, and Z to 3. Can you already see how we can formulate a model now? If so, pause the video now and write your model down. Okay, let's do it together. The objective function is to maximize the revenue that depends on the number of tables and chairs that are produced. I keep using t and c as decision variables instead of x1 and x2 to avoid any confusion due to frequent notation changes. As discussed in a previous video, if you are interested in a general model, it would be reasonable to use x's. For the 2x4s, we have the following constraints that can be derived from our transportation problem perspective. The total supply must be delivered. So we have Z11 plus Z12 plus Z13 equals 6. Note that we have just one supplier for the 2x4s, and the demand for the 2x4s must be met. There is demand in the tables workshop, so Z11 must equal 2T. And also in the chairs workshop, so Z12 must equal C. And of course there is the dummies demand. Following the same lines, we get the following constraints for the 2x2s. Finally, we can define the domains. This completes our model. This might not be the most elegant model formulation, and you may wonder why I spent so much effort on formulating a seemingly complex model for such a simple problem. I did so because there is a lesson to learn from this. The important aspect that I'd like to highlight is the way we have derived a model. Suppose that you had learned about the transportation problem and you were asked to formulate a model for the furniture production problem, a problem you may never have come across before. What we've just seen is that sometimes you can give a problem that you know, the transportation problem in our case, a different interpretation so that it fits, at least partially, to the new problem. Often, a model for the new problem can then be derived by using parts of a model for the problem that you already know. This is a very typical trick in modeling. You'll very often discover that at least some aspects of a new problem are very similar in structure to other, totally different problems. In such cases, you can try to recycle modeling ideas from those other ideas. This remark should draw your attention to the fact that experience is key in modeling. To become good in modeling, you should try to solve as many modeling exercises as you can. Many operations research textbooks provide such exercises. After a while, you will notice that although stories differ, model formulations are familiar to you because of your experience. We are not done yet. Let's put our model formulation aside. Let's rewrite this model. We copy the objective function. With regard to the constraints, we see that we have some constraints that have the form decision variable equals some expression. In such situations, we can substitute the variable throughout the model with the expression in order to eliminate the variable from the model. Let's do this with Z11. Z11 equals 2t. So let's eliminate Z11. Z11 shows up here. The constraint Z11 equals 2t can then be deleted. Do not forget that Z11 has a domain. So we get 2t greater than or equal to 0 from that. Let's put it aside. Let's do the same with Z12 equals C. It shows up here. This constraint can be deleted. And do not forget, Z12 shows up in the domains. Now we see that Z13 equals 6 minus 2t minus c is identical to the constraint that we have here. Hence, we can delete one copy from the model. If you do the same with Z12 and Z22, you'll get this. Z12 shows up here. So we have 2t. Z22 equals 2c. It shows up here. And this is identical to that. Let's do some cleanup in between. We have constraints 2t greater than equal to 0, c greater than equal to 0, and so on, that were derived from the constraints. They can be deleted because T and C have non-negative domain. Finally, let's think about Z13. It occurs only once and it has a non-negative domain. We are not very interested in Z13 because, as you may recall, Z13 is the number of 2x4s that are not used. Therefore, we can delete Z13 from the constraint and write less than or equal to 6 instead of equal to 6. The same can be done with Z23. As a result, we get a model formulation that has fewer decision variables. You'll notice that because of the substitutions we made, we ended up with the very first model formulation that we developed in the previous video. This went pretty well, but we had choices. Let's start again and try something else. Instead of Z11 equals 2t, we could consider t equals Z11 divided by 2, which means the same. With this in mind, we can replace t by Z11 divided by 2. Also, because of c equals Z12, we can substitute c with Z12. So 16 times t is replaced by Z11 divided by 2, gives us 8 times Z11. 16 times a half times Z11. C is replaced by Z12. We can copy the first constraint. This constraint can be deleted. This one can be deleted as well, because we use these two for making the substitution. This constraint looks like this. Now this constraint here can be copied. Here we make a substitution. Two times a half Z11 gives us Z11. Also here we can make a substitution here. and of course the domains. This leads to a new model formulation with decision variables that indicate how many small parts of what type are used for what. A final remark is in order. I'm not proposing the elimination of decision variables in all cases. Sometimes it is helpful, but sometimes the readability of a model suffers from substituting variables with possibly lengthy expressions. So it's up to you to check whether or not it makes sense to eliminate some variables in the way shown.